Our galaxy contains around 400 billion stars and at least 100 billion planets. How many of them are like Earth? Worlds with an atmosphere, complex geology, flowing water, and abundant life. Astronomers seek answers in countless photons racing past the Earth, and in new theories about how planets form and evolve. What they find continues to sharpen one of the oldest debates in science. Is biology a powerful and inevitable result of cosmic evolution, or is life rare in a galaxy shaped by violence and chaos? For thousands of years, humanity has looked to the heavens hoping for a sign that life exists beyond our world. In modern times, the search for planets that might support life has become a central goal in a new era of astronomy. Massive observatories equipped with advanced instruments now make it possible to detect planets in solar systems scattered across the galaxy. A new way of seeing has also expanded the search. In the 21st century, computers began to shape the way we communicate, learn, travel, grow food, buy, sell, and manufacture. The processing power that fits on a single chip doubles every 2 years, a pattern called Moore's Law that has accelerated the pace of discovery. Vast supercomputing centers now analyze streams of data from telescopes, searching for hidden signals and patterns. Astronomers once occupied with long nights in cold observatories now write programs, analyze data, and create models that simulate the birth and development of stars and planets. Instead of settling the question of whether we are alone, their discoveries have reignited one of the oldest disputes in science. The Greek philosopher Aristotle believed that a perfect Earth sat at the center of a small, orderly universe while the heavens beyond were uninhabited, except by gods. Yet others like Epicurus of Samos imagined infinite inhabited worlds among the stars in an ever-changing cosmos filled with endless forms of life. His modern followers believe our galaxy is full of living worlds and even intelligent civilizations waiting to be found. Astronomers have learned that stars like our Sun are common and that planets roughly the size of Earth orbiting at the right distance to support liquid water could number in the billions. Yet another school of thought closer to Aristotle's suggests that life is rare and fragile. Biology, they argue, is too complex and requires conditions so stable that Earth may be an extraordinary oasis in an otherwise barren universe. In the early 1960s, the astronomer Frank Drake, a modern follower of Epicurus, proposed that signs of alien intelligence might already be passing by us as radio signals. Using a radio telescope at Green Bank in West Virginia, he focused on 2 nearby stars, Epsilon Eridani, an orange star just over 10 light-years away, and Tau Ceti, a yellow star about 3/4 the size and mass of the Sun. Since Drake began his work, the search for extraterrestrial intelligence known as SETI has expanded to include hundreds of astronomers, thousands of stars, and a wide range of radio frequencies. Researchers have checked and rechecked Epsilon Eridani, Tau Ceti, and many other nearby stars. So far, after more than 60 years, they have found no repeating messages or unusual signals, but they have not given up because there are so many more places to explore and many new ways to search. While Drake searched for signals, others began to look for the planets themselves. The Dutch-American astronomer Piet van de Kamp looked for small changes in the light of nearby stars. After comparing photographic plates taken over 3 decades, he believed that some stars appeared to wobble as if pulled by unseen companions. One of these was Barnard's star, a red dwarf near the Sun that seemed to move just enough for Van de Kamp to suggest it had planets. He also reported wobbling motion in other stars such as Lalande 218561 Cygni, and again Epsilon Eridani, which is the 3rd closest visible star to us. However, his findings did not hold up to later testing because of an error in the telescope itself, and his results were widely rejected. Still, his belief that the Milky Way is filled with planets took hold among astronomers. What scientists began to find next was even more surprising. In the winter of 1991, engineers at the Arecibo radio telescope in Puerto Rico discovered structural problems in the instrument and decided to keep it fixed in one position. This gave the astronomers Alex Wolszczan and Dale Frail the chance to observe a special kind of collapsed star called a pulsar that spins rapidly and emits a flash of energy with every rotation. One pulsar they studied flashed about 6 times each second, but not at a steady pace. It flashed faster and slower in a complex rhythm that could only be explained by the gravitational pull of 2 rocky planets. A third smaller world was later found orbiting the same star. These became known as burned-out zombie planets circling the remains of a dead star. They were not the only ones. The oldest known planet, called Methuselah, orbits above the Milky Way. It is more than twice as massive as Jupiter and circles a pair of dead stars, a white dwarf and a pulsar once every 100 years. Discoveries like these challenged long-held theories about how planets and solar systems form and evolve and how worlds like Earth come to exist. The leading idea known as the solar nebula model dates back more than 2.5 centuries. It describes how the death of a giant star can trigger the birth of new ones. When such a star explodes, the shock waves cause a massive cloud of gas and dust to collapse under its own gravity. As the cloud contracts, its center grows hotter, forming a swirling storm of dust, gas, and ice crystals. Eventually, temperatures rise high enough for a new star to ignite at the core. The surrounding material flattens into a vast rotating disk where fierce stellar winds push lighter gases to the outer regions, leaving heavier dust and rock near the center. As the winds fade, the process of planet formation begins. Beyond a certain boundary called the frost line, planets grow rapidly as they collect ice gas and dust. Inside the frost line, smaller solid bodies called planetesimals form from clumps of rock and metal. These objects collide and merge over time to become the planets we see today. If our solar system served as a guide, astronomers expected to find rocky planets like Earth, Venus, and Mars, forming in the hot inner regions where iron and silicon could melt and combine into solid planetary cores. Farther out beyond the frost line, gas giants such as Jupiter and Saturn were expected to form in the colder zones where water, methane, and ammonia condensed into ice and built up into massive planets that captured lighter gases through gravity. Even farther away, icy giants like Neptune and Uranus would take shape after the larger planets had already gathered most of the available hydrogen. It did not take long for new discoveries to challenge this traditional view as a new age of planet hunting began. Looking toward the southern constellation of Pictor, astronomers observed a young star accompanied by a massive newborn planet. The star, called Beta Pictoris, is twice the size of our Sun, 50% hotter, and nearly 9 times as bright. Its thick disk of gas and dust stretches far beyond the orbit of Pluto. Nearby, passing stars tug at this disk, causing waves of turbulence while the giant planet orbiting at twice the distance of Jupiter adds to the chaos. A NASA simulation shows the planet's gravity hurling streams of debris toward the star in a spiral pattern, while a side view reveals pressure waves created by its slightly tilted orbit. These waves increase collisions between icy and rocky fragments throughout the disk. Such findings forced astronomers to rethink their models of solar system formation. They realized that many factors affect how planetary systems develop, including the size of the original nebula, the type of star at the center, and the gravitational influence of neighboring bodies. As more planets were discovered, it became clear that planetary systems are far more dynamic and diverse than once believed. Several research teams focused on detecting tiny shifts in starlight caused by orbiting planets. When a star moves toward or away from Earth, its light changes color, shifting slightly from blue to red and back again. This subtle motion can reveal planets orbiting very close to their stars, even if those systems are far from us. In October 1995, Swiss astronomers Michel Mayor and Didier Queloz used this radial velocity method to study the star 51 Pegasi, located about 50 light-years from Earth. The star is similar to our Sun but slightly larger and more massive. Its wobbling light revealed the presence of a giant planet about half the mass of Jupiter, but 1.5 times its size. The planet, now known as Dimidium, surprised scientists because it orbits extremely close to its star, 8 times nearer than Mercury is to the Sun. This scorching gas giant reaches temperatures more than 1,500 degrees Celsius, far hotter than Jupiter. How did such a planet end up so close to its star? Dimidium was just one of many strange worlds discovered patrolling the inner regions of their solar systems. Some were large rocky planets with deep oceans, others were small gas planets, frozen worlds, or planets covered in molten lava. With each discovery, our own solar system began to look increasingly unusual. To understand the full variety of planets and their formation, astronomers needed to observe entire populations of stars in greater detail. In 2009, they began using a new planet hunting approach that combined spacecraft telescopes and supercomputers to measure even the smallest changes in starlight. The question remained whether these efforts would prove Earth to be truly unique, or reveal that inhabited worlds are common throughout the galaxy. Astronomers directed the powerful Kepler telescope toward a region containing about 500,000 stars as far as 3,000 light-years away. Their goal was to detect the faint dimming of a star when a planet passed in front of it. For this technique to succeed, the planet's orbit had to line up perfectly with the telescope's line of sight. Using this transit method, Kepler, scientists assisted by volunteers around the world, identified nearly 2,700 new planets. Kepler was later succeeded by the transiting exoplanet survey satellite known as TESS, which scans almost the entire sky, focusing on the brightest stars close to Earth. The planets revealed by TESS have shifted opinions once again toward Aristotle's idea of a rare and special Earth. Transit surveys tend to discover large planets that orbit close to their stars. Together with the Hubble Space Telescope and advanced ground observatories, these missions have revealed many hot Jupiters similar to the one at 51 Pegasi. Some of them face such intense solar winds that their atmospheres are being stripped away. Based on Kepler's data, scientists estimate that Jupiter-sized planets and larger make up less than 1/5 of all known planets. The most common type, accounting for just over half, are Neptune-sized worlds with rocky or icy cores, surrounded by thick layers of water, ammonia, and methane gas. Some theories suggest that deep within these planets, carbon forms into massive diamond rain that falls toward their cores. The planets detected so far mostly orbit close to their stars. Some may be former Jupiters that lost mass, or gas giants pulled inward by the gravity of larger neighbors. Within the data, researchers noticed a class of planets smaller than twice the size of Earth, known as mini-Neptunes, that transition into denser rocky worlds. These super-Earths make up about 18% of all known exoplanets. One example is Kepler 22b, a super-Earth located in the habitable zone of its star. It may be a water world covered by a deep global ocean surrounding a heavy rocky core. Another example orbits the star 55 Cancria planet, almost 8 times more massive than Earth, with a surface temperature near 2,000 degrees Celsius. Kepler 452b has an orbit similar to that of Earth and circles a star much like the Sun, but the planet itself is roughly 5 times larger, making it a cloudy world more like Venus. Earth-sized planets account for about 11% of the total, yet being Earth-sized does not guarantee habitability. For instance, the TESS satellite found the planet HD 21749c, orbiting an orange star about 70% the size of our Sun, just 53 light-years away. It completes one orbit every 8 Earth days with surface temperatures around 400 degrees Celsius. A neighboring planet in the same system 23 times Earth's mass is a hot mini-Neptune with cloud temperatures of about 150 degrees. Another planet called LHS 3844b, only slightly larger than Earth, has a year that lasts just 11 Earth days. Its surface is likely covered in molten lava. The Sun-like star Pi Mensae hosts a planet twice the size of Earth, where surface temperatures exceed 900 degrees Celsius. Despite these inhospitable examples, scientists remain hopeful. As instruments improve, astronomers continue to find hints of truly Earth-like planets. Red dwarfs, the most common stars in the galaxy, are small, cool, and faint compared to the Sun, but their planets orbit close and complete their years in just a few days. One such star, Proxima Centauri, is the closest to our solar system. It has only 12% of the Sun's mass and shines at about 2% of its brightness. After nearly 2 decades of careful study, astronomers confirmed at least one Earth-sized planet orbiting it called Proxima Centauri b. This world completes an orbit in just over 11 days at a distance where liquid water could exist. However, Proxima Centauri is an active and stormy star releasing intense ultraviolet X-ray and gamma radiation that could destroy any atmosphere its planets might have. Proxima Centauri b belongs to a class of worlds known as eyeball Earths. These planets orbit so close to their stars that they become tidally locked, with one side always facing the star and the other always facing away. One side is scorched and dry, while the other is frozen in eternal night. The region between the two may form a twilight band where temperatures are moderate enough to allow liquid water and perhaps life. Another promising system is TRAPPIST-1, an ultra-cool dwarf star that hosts at least 7 rocky planets all packed into tight orbits. Each world is made of rock, but their densities suggest that many contain large amounts of water. The star itself is tiny, only about 11% the size of the Sun, and emits just a small fraction of its light. Yet the planets have another source of heat. Their close spacing causes them to tug on one another's orbits, creating internal friction that warms their interiors. The innermost planets are likely hot and steamy, while the outer ones may be frozen. The fourth planet from the star, slightly smaller than Earth, could have conditions suitable for liquid water, though it is unlikely to support an advanced civilization. As astronomers continue their work using both space-based telescopes and ground instruments, they are beginning to identify more distant planets farther from their stars. These discoveries are reshaping our understanding of how solar systems form and increasing the chances of finding planets capable of supporting life. Computer models show that soon after the Sun was born, Jupiter formed beyond the frost line in a region rich with gas and ice. Its growth quickly cut off the supply of material flowing toward the inner solar system, slowing the formation of rocky planets. Using powerful simulations, scientists have mapped Jupiter's path among countless small bodies that filled the early solar system. The blue rings in the models trace Jupiter's orbit, while bright flashes mark the collisions of smaller planets in formation. As Jupiter grew, it responded to both the pull of the Sun and the push from Saturn. Its orbit began to shrink in a motion scientists call the grand tack, similar to the way a sailboat turns into the wind. During this inward journey, Jupiter either swallowed smaller objects or flung them toward the Sun, creating chaos in the early solar system. The models suggest that Jupiter reached as close as the orbit of present-day Mars before Saturn pulled it back outward. This migration reduced the mass of the inner solar system and may have destroyed or absorbed any large super-Earth that might have formed. Ironically, Jupiter's violent passage may have also delivered the icy material that seeded Earth with water and organic compounds. The impacts that followed continued to shape the planets. Mars may have lost its early chance to sustain life, while Earth faced its own catastrophic event. Scientists believe that a Mars-sized body named Theia struck the young Earth. The collision did not destroy our planet, but instead threw a vast amount of debris into orbit that later formed the Moon. Over time, the Moon's gravity slowed Earth's rotation and stabilized its tilt, creating tides that helped mix the oceans and set the stage for life. Jupiter continued to play a vital role, working with Saturn to push Uranus and Neptune to the outer edges of the solar system. This movement disturbed the orbits of millions of comets, sending them toward the Sun. Many of these icy visitors collided with Earth, delivering more water to its surface. One of the first planetary systems studied by both Piet van de Kamp and Frank Drake Epsilon Eridani turned out to resemble our own in surprising ways. It has a distant cloud of icy debris similar to our Oort cloud, a second belt of rocky objects like our Kuiper belt, and a giant planet orbiting near a ring of asteroids, much like Jupiter near our main asteroid belt. Astronomers cannot yet confirm whether a true Earth-like planet exists there, but it remains a strong candidate. The search for Other Earths has long focused on the habitable zones around stars where planets can maintain liquid water and stable climates. In these regions, a planet can develop an atmosphere, active geology, and ocean systems that may give rise to life. Yet the history of our solar system shows that creating a habitable world requires a rare combination of events and a great deal of luck. For that reason, some astronomers now propose widening the definition of habitability. The most suitable planets for life, they suggest, might not be exact copies of Earth, but what they call superhabitable worlds. Such a planet would be about 1.5 times the size of Earth, orbiting a stable orange K-dwarf star that burns cooler and lasts longer than the Sun. It would possess abundant water, a molten interior generating a strong magnetic field, and a thick atmosphere that shields its surface from harmful radiation. Geological activity would shape gentle landscapes, with few mountains and long-term stability, allowing chemistry and energy to combine in ways that favor life. From the thousands of planets discovered so far, scientists have identified about 24 that could fit this description. Future telescopes in space and on the ground will search these worlds for gases such as oxygen and methane that could signal biological activity. Some of the largest new observatories may even capture direct images of distant planets, revealing their climate rotation and seasons, oceans, and perhaps vegetation. If such evidence remains out of reach, some may continue to argue, like Aristotle, that Earth is truly unique. Others, inspired by Epicurus, believe that with so many planets in the galaxy, it is inevitable that life exists elsewhere. If intelligent life has evolved here, it may have evolved somewhere else as well. Perhaps those beings are already studying the faint light of a yellow star in the Milky Way and noticing a small pale blue dot circling it. They may wonder if they have found another Earth, one capable of life, and maybe even communication across the vast darkness of space. Thanks for watching.